Good morning. Today, um, we will talk about type 2 error and power. So remember in type 1 error, we say that to reduce type 1 error, one way is to change the limits. Okay? So remember the limits at first was x bar greater than 69 and x bar smaller than 67. And the error here was about 9.5% or 0.095, right? But if you just change the limits, so it's something like this. Just plot the probability distribution. Okay, let me just make it longer here. So it was just 60, 67, and 69. So the error was the area here. Okay, the error was area here. So the mean was 68. So if you just change the, let me just change the color as well. So if you just change the limits to 73 and 63, where 63, so then the error becomes this blue shaded region, which is much more smaller. So let's see what is that. Well, if you just calculate this 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 shaded area, it turns out that it's practically zero. Okay, so there's no error if you just reject the H0. So again, alpha is probability of type 1 error, right? Type 1 error, and this is equal to probability of reject H0, okay, given that H0 is true, okay. So if you just reject H0, then you don't make an error, okay, here, because alpha is here, alpha is just equal to 0, okay. Is there any problem with this? Well, what happens if you don't reject H0? Okay, so if you don't reject H0, so if you reject H0, then there is no problem with that. Okay, so if you reject H0 and if you decide not to buy the cases, then there is no problem. But if you don't reject H0 and decided to buy the items, well, there must be some problem, okay? So then you will probably purchase the cases whose mean is 66 or whose mean is 70 millimeters, okay? So this is something you don't want. Let's try to illustrate this. So consider the case where you decided that mu is equal to 68 millimeters, even if the real parameter is 70 millimeters. So what does it mean? Even if the mu is equal to 70, so even if the factory is producing with this mu, you don't reject H0, okay, you don't reject H0. And so you think that, well, the real me is equal to 68 and decided to buy, okay? Let's try to illustrate the probability of this one. So let's find the probability of this situation. So what is this probability? Probability of by a large amount of cases, but in fact mu is equal to 70 millimeters. So what does it mean? It means probability of do not reject H0 when mu is equal to 70. So when you do not reject H0, so remember, we will just reject H0 if X bar is smaller than or equal to 63 or X bar is greater than or equal to 73. Okay, so if X bar is in between, just like this, if X bar is in between, then you don't reject the hypothesis. So how to find this probability, remember, you will just convert this to standard number, right? So 63 minus mu divided by the standard deviation of x bar. Again, 73 minus mu divided by the standard deviation of x bar. And here we also have x bar minus mu divided by 0.45. Given that, well, the factory is now producing with some difference mu, okay, with 70. Mu is equal to 70. Okay, now, well, mu is equal to 70, so what I will do is, instead of mu that we see here, I will just plug in 70, okay? So I will get scalars here, And what is this? This is simply z, right? This will be z. So let's see. I have the probability of z being between minus 15.55 and 6.66, which is equal to 1. Okay, so what is this? This is beta, or probability of type what? Type 2 error. Okay, probability of type 2 error. So what was probability of type 2 error? Probability that don't reject H0 given that H0 is not correct. Okay, so this probability of making errors is equal to 1. So if you don't reject H0, then with probability 1, you are making an error. Okay, so so after the test, if you reject H0, then you are not making any error because we have found that alpha is equal to 0. But if you don't reject H0 and say that okay, that's a good thing to buy, then it turns out that the probability is very, very high that you are making an error. Okay? So if you just change your rejection region from this, okay, to this, then if the real mean mu is equal to 70 millimeters, okay, so if the factory is producing with some mean other than you just want with the mean that you different than the mean that you want. So remember, our original mean, our requested mean was 68 millimeters. So if this is the case, then you are fine. But they are producing with something different than that. Okay. So if the real mean is equal to this one, if the factory is producing with this mean, and if you don't reject hypothesis, then you are almost always making an error. Okay. And this error is in fact type 2 error. Do not reject H0 when it is not true, when some other mean is true. Okay. So, well, as you see, in order to calculate beta, which is the type 2 error, we need to specify a particular value for mu. Okay? So in our case, in this particular example, we just take this as 70, okay? Because if you want to calculate this probability, the probability of do not reject H0, given that H0 is not true, right? So H3 is not true does not give you a value for mu. Okay, so in order to calculate the probability, you need a value for mu. Okay, so in order to calculate this, we need a value for mu. So H0 is not true is not sufficient to calculate a probability. So in the previous example, we just set mu equal to 70. Hence, in general, we define beta as not only beta, but we define it as beta of mu, which indicates that it depends on the value of the selected. Okay, so for example, if you just set mu is equal to 69, then you will get another value of beta. Okay, you will get another beta. Okay, now let's try to set our critical region to its original values, okay, and try to see what happens to the error now. Okay? So for example, for mu is equal to 70 or mu is equal to 66 or mu is equal to 68.5. Okay, so you can do some of these at your home at the comfort of your home, and so now we will solve uh, three of them and see the associated plots with each of three values of mu. Okay. So now let's try to see what happens. So let's try to see what happens in terms of probability plots. Okay. So remember, we say that type 2 error is probability of not rejecting H0, which means it's between 67 and 69. Okay, given that mu is equal to 70, right? So this is H0 is not correct, or given H1 is correct. Okay, so as remember we said that, well, H0 is not correct, right? Remember, we said that H3 is not correct, is not enough to calculate the probability, hence we assign a value. Here we assign mu is equal to 70. Okay, so what is the probability? Which probability we need? We need to find the probability of x bar being between 67. So let's say this is 67 and this is 69. So let me just change the color. So the probability that x bar is between this 67 and 69. Okay? But it says that, well, mu is equal to 70. So mu is equal to 70. Just look at here. Mu is equal to 70 is here. So this one says that calculate the probability, okay, using the distribution, okay, the distribution of x bar. The distribution of x bar is the one on the right. Okay, so you need to take care of this distribution, okay, because it says that, well, mu is given as 70. So what we will try to do is find the probability that x bar is between 67 and 69, okay, under this probability distribution. So what is that probability? That probability is this small region, right? So the probability of x bar being 67 and 69 is this region, okay? So let's see, what is that probability? 67, 69. So let's find this probability mathematically. Given mu is equal to 70, just plug in mu is equal to 70 at here and here and here, okay? So this one becomes z, and the values here is minus 6.67, and the right-hand side is minus 2.22. So this probability is equal to 0.0132. So this is almost equal to 1 point, not almost, but this is equal to 1.32%. Okay, so the probability of making a error, type 2 error, is only 1.32% when mu is equal to 70. Remember, the alpha was equal to, I'm not sure, but it's something like 2.5%, okay, under this setting. And beta here is 1.32%. That's pretty good, right? Now just try to make the same thing, okay, when so in the previous one, in the previous slide, it was mu is equal to 70. Now we will try to calculate beta with a different mean. Mu is equal to 66, okay? So probability of type 2 error with mu is equal to 66. So what is this probability of do not reject H0? When you do not reject H0, when if x bar is between 67 and 69, given that mu is equal to 66, okay, I just plug in 66 here, here, okay? And so if you just plug in 66 here and divide it, of course, by 0.45, you get a z here. And this is equal to z is between 2.22 and 6.69. It's also equal to, just look at this one, it's the same value, okay, 1.32%. So let's try to understand this from the figure as well. Again, I will try to find the probability that x bar is between 67 and 69. Okay, so 67 and 69. I will try to find this probability. Okay, so the probability that XR is between 67 and 69, given that mu is equal to 66, what does it mean, mu is equal to 66? It means that just use this distribution, okay? So this is your distribution. X bar is distributed with this distribution, and you have to find the probability using this distribution. Okay? So the probability that X bar is between 67 and 69, okay, under this distribution, and the result is equal to 1.32%. Right? It's the same. So what does it mean? Well, the intuition is that, so remember 68 and the alternative was 70 in the previous slide. In this slide it's 66. Okay, so the difference is 2. So difference is 2. So as you might guess, so if the 68 minus the alternative mu, okay, so if mu is 66 or 70 or 71 or 67, well, the result will be the same, okay? So it just depends on the distance between the alternative hypothesis and the original hypothesis or the null hypothesis. Let's find the same probability when mu is equal to 68.5, okay? So alternative is 68.5. Now again, my calculation is, so remember, so I'm just writing beta of 68.5. Why? Because as we said, um, you can calculate the type 2 error only by giving a value to it, right? So this is probability of type 2 error given that mu is equal to 68.5. So just go back. So I'm just calculating the same thing, okay, with different mu's, okay? So let me remove all of them. Okay. So just look at this. So in the first one, I'm just calculating the error, probability of type 2 error with mu is equal to 70. In the second one, I'm just calculating it with mu is equal to 66. And now I'm just calculating it with 68.5. Okay, I'm just making the same thing, exactly the same thing. The only difference, as you might guess, I'm just putting 68.5 here because the mu is now 68.5. And it turns out that this probability is equal to 0.866, which is equal to 68.6%, which is pretty high, right? And let's, on the figure, let's illustrate this. I'm trying to find the probability of X bar being 67 and 69. So 67 is here, okay, 67 is here, 69 is here, okay. I'm trying to find the probability that X bar is between 67 and 69, okay. So the probability that X bar is here. So what is the distribution? The distribution is H1, okay, under H1, if mu is equal to 68.5. So what is the region? The region is, or the shaded area is this part, right? Because you are using this distribution, right? Okay, this is our distribution. This is our shaded region, and this one just gives you the beta. Okay, so understanding it here is much more better than the previous one because here we only have a very small portion of area here, which is equal to what? 1.32%. Okay, so here this shaded area, it turns out to be you have 86.6%. Right? Great. So we can generalize this, well, we said this, to see that, well, beta values will be the same when mu is equal distance from the original hypothesis, the null hypothesis, which is 68. Well, we also see that, well, beta becomes smaller, okay? So type 2 error becomes smaller if the distance between the mu that you set as the as the value of the alternative hypothesis and the original hypothesis. So this is H0, let's say this is H1, okay? So if the distance between them increases, then beta gets smaller, okay? So if H0 gets away, sorry, H1 gets away from H0, then your type error becomes smaller. But as your alternative hypothesis, the value of mu at alternative hypothesis gets closer to the value of the null hypothesis, then the error beta becomes larger. Okay, that's because, well, it becomes more and more and more difficult to identify the difference between two means if both means are close to each other. Okay, so if the alternative mean and the mean at the null hypothesis are very close to each other, then it's very, very hard to differentiate between them. That's why your type 2 error becomes, uh, it just increases when both means, both values in different hypotheses just gets close to each other. So if you just go back and look at type 2 error with type 1 error, well, for any fixed sample size, okay, so if you just fix n, then one error type increases. When one error type increases, the other one type decreases. So if alpha increases, beta decreases, or so if alpha decreases, then beta increases, okay? So if you just want to decrease both of them, what you should do is just increase the sample size, okay? If you increase the sample size and keep everything constant, then both of the errors just decrease. Well, so it's good to control the probability of these two types of errors. Please note that these errors, alpha and beta, okay, the probability of two type of errors, you just determine them before getting into making any measurement. So what I mean is that please recall that we don't use any x bar observed, or we don't use any z observed or t observed when you're just calculating alpha and beta. Okay, so alpha and beta just refers to the design of the hypothesis. So before making any measurement, you just determine alpha, beta, and other parameters so that you just define the probability of the errors you should make before getting into the measurement. Okay, so alpha and beta has nothing to do with x bar observed, z observed, or t observed. They just depend on the critical region. Okay, so you just determine them before making the measurements. So for a given sample size, you cannot control both. Okay, you cannot reduce both, or let's say. So what we do is we use a hypothesis testing procedure that controls the probability of type 1 error, okay, and guarantees that it cannot exceed a given small probability of alpha. In fact, this is what we did so far, right? So at the beginning of a question, we said that let's take alpha is equal to 0.05. So what is alpha? Alpha is the probability of type 1 error, right? So what we do in each question, well, we just fix alpha and say that just take alpha as 0.05, that's our type 1 error, and make your calculations, okay? So in what we do in hypothesis testing is that we just determine first the value of the probability of type 2 error, okay? And type 2 error, okay? And when you just determine the type 1 error, then the beta error follows, okay? So, so in general, what happens is that you just want the alpha, the type 1 error to be equal to this one, okay? And you say that, okay, I want beta or to be, for example, less than 0.20. In order to achieve this both, okay, you just find what? Find the number of experiments, okay? So you just find the number of experiments which makes you, which enables you to keep your type 1 error at 0.05 and your type 2 error at 0.20, okay? But if you determine alpha, okay, and if you are just given a value of n, then uh, your beta can be calculated using alpha and n. Okay, but in general, what, for example, in hypothesis testing of the medical doctors in their research, what they do is, well, I need an alpha of 0.05 And well, I want my type 2 error to be less than 0.20. In order to make this, how many patients, how many observations, or how many experiments do I need? That's what the medical doctors doing in their research. Okay. We will do the same thing in statistical quality control, for example. What you're trying to do is you're trying to make some inference on the means of, or on the proportions, or on the variances of the parameters of a machine in a factory. So what you want to do is you want to make a hypothesis test whether the process is under control or out of control. There, what you do is you just set an alpha value, and then you just set a beta value, and then try to find n, which is the number of samples that you should take from the products. Okay. Okay. So for the previous example, uh, recall that we say the critical region is x bar is smaller than 67 and x bar is greater than 69. So instead of this, okay, so assume that we are given alpha, right? So in the previous question, we are given the critical region directly. We are not given alpha. Remember, remember, generally what we do is we are just given alpha. We are just given alpha, and we just calculate uh, the critical region, okay? So given alpha, we just find the critical region. Now in this question, so this is the previously, this is what we are doing, okay? Previously given alpha. So now we are given alpha, sorry, not given alpha. Let me just erase this part. So in this question, let's say, so in this question, uh, given critical region, we just found what? Find alpha or type 1 error, okay? Probability of type 1 error. Now, the question just goes back and says that, okay, so now, given alpha, again, it just asks us find the probability of type 1 error. Okay, now let's try to find this. So my intuition is that, well, the question gives you alpha and asks the probability of type 1 error. But by definition, alpha is the probability of type 1 error. Okay, so what I expect to see is the probability of type 1 error will be equal to 0.05 as well. Let's illustrate this, okay? So now, since alpha is given, I should find a critical region, okay? So that the critical region will be C1 and C2, so that if x bar is smaller than C1 or x bar is greater than C2, we will reject the hypothesis, okay? So we will find probability of x bar smaller than C1 or plus x bar is greater than C2, that will be equal to 0.05, okay? So that is, I will find something like this. So this is my, this is the distribution of x bar, okay? So this is what? This is 68. I will find C2 here, okay? And there is a shaded region there. I will find C1 here. There is a shaded region here, okay? So the shaded region will be 0.025, okay? And the shaded region here is 0.025, and sum of them is equal to 0.05. So first find C1 and C2, okay? So remember from our previous arguments, you can just find C2 as mu plus Z sub 0.025 times the sigma of x bar, which is equal to 68.74. Okay? So similarly, you can also find the C1, which is 67.26. So it's something like this. So here you have, so this is 68. Okay, so this is 68.74, right? And this is 67.26, okay? So this is equal to 0.025, and this is equal to 0.025, okay? Now the type 2 error is, what is the probability of x bar is greater than 68.74 or x bar is smaller than 67.26 given that mu is equal to 68. So what is this? Just look at this one. Well, it's the probability of, okay, so let me just change the color. So this one, okay, is equal to the area here, and this one, okay, is equal to the area here, right? So this is simply equal to 0.05, right? So that's exactly what is given in the question as your alpha value, okay? So again, alpha value is the significance level or the probability of type 1 error. That's what you are given at the beginning of the question. So by giving alpha, what we do is we just set the probability of type 1 error to a predetermined value. Okay. So now let's calculate beta when the real mean is equal to 70. Okay, so I will calculate the type 2 error, probability of type 2 error. Okay, type 2 error when mu is equal to, given that let's say mu is equal to 70. Okay, so what's the probability of type 2 error? Do not reject the H0. Okay, so when you do not reject the H0, if x bar is between 67.26 and 68.74, I want to reject the H0, given that the true mean is equal to 70. So what I will do is I will just plug in mu here, here, and here, okay, and calculate the probability, right? You see this? 67.26 minus mu, this mu is equal to 70, okay, so this is 70, and this is 70, and this is 70 as well, and this will be equal to what? This is equal to z, right? And it turns out that this is equal to 0.0026, which is in fact 0.26%, which is very, very small, okay, very small for this example. So if mu is equal to 70, and if you just set alpha, remember, if you just set alpha equal to 0.05, then it turns out that beta for 70 is equal to 0.26%, which is in fact very small. The last thing that we will talk about is the power of a test. Okay, so power of a test is very simple. It's just 1 minus beta. Okay, so the power of a test is equal to 1 minus beta. Remember what is beta? The probability of type 1 error, which is, sorry, do not reject, do not reject H0, given that H0 is not true, right? Or H1 is true. So what is 1 minus beta? 1 minus beta is equal to probability that reject H0, okay? Given that H0 is not true, okay? So the power is related to, in fact, it's the power of the test to say wrong to something which is wrong, okay? So if you can reject the H0 when it is not true, then that's the power of the test. That probability is the power of the test, okay? So it's correctly rejecting a false H0. So it so the power of the test is the ability of the hypothesis to differentiate between two hypotheses. So if the two hypotheses are very close to each other, remember, for example, if it is 68 and 68.5, then the power will be very low. Okay. So a good testing procedure should have a small level of significance and a large power, or a small type 2 probability of type 2 error. Okay, so the previous example where we have alpha is equal to 0.05 and beta was equal to 0. I don't know what, 26%, the power is 0.9974. So that's a pretty large power. Okay. Um, so for the previous example, what you can do is you can just calculate the beta for different mu values, okay, and just plot 1 minus beta to see the power at different values of mu, okay. You can just prepare a sheet, an Excel sheet, okay. So this is not an assignment, but this is a good exercise to make at home. So what you can do is you can prepare a simple Excel sheet for calculating the power of the test in example 2 in the previous example, okay, in the previous example, right, for many different values of mu under h1. Then just graph the power function, just plot it under for different mu values. So one final remark is, sorry, as I said, um, in real life, for making the test, what people do is they just determine the level of alpha, determine the level of beta, okay, and then find the required n, okay, how many samples do we need? So how do we find it? Well, this is the general formula that one for that one, okay? So z alpha, so for example, in the previous example, I just said alpha is equal to 0.05, for beta, I said that's 0.20. So sigma square, remember we said that we know sigma square, and divide it by delta square. And what is delta? Well, delta is, so mu is equal to mu zero, that's H0. Mu is equal to mu zero, which is the value at the null hypothesis, plus some delta. Okay, so that's H1. Right? So mu zero plus delta is the value of the mu at the alternative hypothesis, and mu zero is the value at the null hypothesis. Okay? So this delta is the difference between the value of mu's in H0 and H1. Right? So this is the needed sample size for a single-sided test. And this is similarly, this is the value of the sample size for a double-sided test, for a two-sided test. Okay, again, so what the test is, the difference between means is equal to d0 versus the difference between the means is equal to d0 plus some delta. Okay, so that's all for the type 1, type 2 errors and the power of the test.